My apologies for the technical difficulties, and this is sort of the second time, so I'd like to thank the organizers and the session chair for allowing us to present in this session now, given the technical difficulties we had earlier this week. So my name is Bri-Mathias Hodge, and I'm presenting today because Wallace Kenyon couldn't make it, and so I'd like to present on coupled transmission and distribution simulations for assessing distributed generation response to power system faults. So Wallace is a PhD student at the University of Colorado Boulder, where his focus is on the stability and operation of high penetration inverter-based power systems. And so the co-authors are myself and Bri-Mathias from NREL. And so the goal here is to look at the impact of growing amounts of distributed generation on the power system. And so in the Western interconnection of the United States, which has a peak load of around 200 gigawatts, we right now have about 10 gigawatts of distributed generation. So this is a very significant amount, obviously. And most of the time when we're doing these sort of transmission level simulations, we take these thousands or millions of distributed generation units and aggregate it to higher voltage levels. Some of the issues with this is that it obscures voltage diversity, and so the voltage isn't the same at every inverter on the system, even though that's how we're modeling it. Equipment diversity, they're not all the same inverter, for example. And we often treat these just as a negative load, which also obscures their impact on dynamic performance. A further issue is that we obscured the ride-through compliance. So that's going to be the focus of the presentation here today. So ride-through is a very important aspect of distributed generation. And so we want to look at different sort of levels of ride-through compliance and how that will impact the aggregated DG response for disturbances. And so the IEEE standard, which governs this ride-through performance, is IEEE 1547. And the original case in 2003, we'll call the pessimistic case. So here, the original intent was there were very small amounts of distributed generation on the system, and so they were encouraged to get offline very quickly whenever there was an issue, and this was primarily for lineman safety. However, it's now been revised a couple times, and the latest revision is IEEE 1547-2018, and this allows for basically 3 different categories of ride-through compliance. You see here Category 1, Category 2, and Category 3, and the goal here is to, because we now have larger amounts of this distributed generation, we expect it to play a role in continuing to maintain system operations. And specifically, we want to look here at what is the impact when there are large faults in the system. So here we're looking at a model of the entire Western interconnection of the United States, and we have a fault here at Lugo, which is in Southern California. And we can see there are areas, even all the way up into Oregon and Washington, where we see voltages that are now below sort of standard levels from a fault that's thousands of miles away. And so this is very important that we can understand not only the impact of these faults in multiple locations, but the impact on the distributed generation that is then connected in those locations. And so one of the things we're going to talk about here is how long these faults basically persist and the impact of them. And this is a very common phenomenon in the Western interconnection known as fault-induced delayed voltage recovery, or FIDVR. And so basically what happens here is we have a fault on the system, and so we have some low voltage levels and a lot of inductive loads, so primarily single phase residential AC air conditioners will stall. And this creates things like here on the right, where we have that same Lugo fault at 500 kilovolts. And then there are buses on the system, such as the LS 66 kV that you see in that sort of light blue case, where this produces low voltages for over 10 seconds. So that's far beyond most of the ride-through capabilities and requirements of the distributed generation. So even though we have these new sort of requirements, some of the events can actually exceed those and then give us potential issues for reliability. And so the primary goals of this study were to be able to couple a transmission level simulation with a distribution simulation so that we can assess the impacts of some of these different IEEE 1547 ride-through standards and look at the impact of them on the Western interconnection of the United States during fault events. So at the time of this work, there wasn't a federation protocol between PSLF and OpenDSS. And so what we did was we created this simulation methodology, and basically we'll run the transmission simulation under some different scenarios. And then we will extract the voltage profiles from the local buses and then send those into the distribution simulation at sort of the feeder head. This allows us then to assess the impact on the DG. Does it trip off? Does it not trip off? And then we can feed that back through into the transmission simulation so that corrective actions can be taken if there is a loss of this distributed generation. So we can do this in a couple different sort of orders. We do here the looped or iterative methodology, but it's pretty interesting just to look sometimes at what happens if you do a single pass through as well. And so for the transmission simulation setup, here we're using PSLF with a case for the Western interconnection in the United States. So this is a heavy summer 2023 planning case from WEC. And what we use here is the composite load model with generation. And so this does give an aggregate response for DG. And what we are looking at in terms of fault is a three-phase fault on path 61, so that's the Lugo bus, at the 500 kV level. And so this was chosen because this is one of the more critical paths in the Western interconnection. We take that information from the transmission side and we pass it down to the distribution side, and we utilize OpenDSS here using existing feeder topologies that we've collected from utilities in the Western United States. And so this just shows on the right the voltage profile for a commercial/residential 12 kilovolt feeder, and you can see sort of where the voltages at the end of the feeder are starting to get to places that are pretty close to tripping events. And so we are looking at the inverter response as it determines the ride-through compliance. And so we matched the composite load model in PSLF with a single feeder and then scaled the distributed generation on that feeder in a corresponding manner. So here on the distribution side, these are quasi-static time series simulations. Basically, we take that bus voltage from the transmission level and then pass that on to the distribution level and simulate that. In order to analyze this, we're going to take a look at two different metrics. One's pretty standard, right? Is the frequency of the system. And so here we're taking a weighted average of the frequency over the Western interconnection. And then the second is a metric that we devised called the volt-second metric. Basically, what we're trying to do here is we're trying to understand the amount of time that we're having under voltage conditions. So not only the magnitude of that, but then also the duration of those. And so if we do one of these single pass simulations, we can see varied responses from the aggregated distributed generation based on which IEEE standard is applied. So here on the left-hand side, you can see at the time of the fault, you experience this drop in DG output in all these cases. In the case of the 2003 pessimistic case, basically, almost everything comes offline almost instantaneously. So this is, a loss of 4 gigawatts of distributed generation at one time. So remember the peak load in this case is about 200 gigawatts. So that is a very significant drop in generation. You can see varying responses based on the other IEEE 1547 standards. The category 1, for example, has a larger amount dropped. Category 2 is slightly better. And then category 3 has, retains roughly 80% of the generation or so. And so this is over 123 different feeders with over 6,000 different individual inverters explicitly. So that's about 4.2 gigawatts of DG. And then you can see here from the numbers below how much is lost. So it ranges basically from 4,000 megawatts to the 1547-2018 category 3, only 1,500 megawatts lost. Here you can just see some of the voltage profiles at different locations. So at the top here, you see the voltage profile at that location where we have the fault. And so in this case, actually, after about 2.5 seconds, the 2003 pessimistic case simulation diverges. So this doesn't mean necessarily that the system went unstable, but it's obviously not a good sign either. And then you can see how the voltage sort of recovers for those other cases. You can see the voltage is still at a pretty low level, recovering at just over 0.9 for the category 1 and 2 cases, whereas for the category 3 cases, we're recovering much closer to a 1 per unit. We can also quantify this in terms of the volt-second score, and you can see that the volt-second score, so basically this is the summed deviation of voltage over time, is far less for category 3 than it is for categories 1 and 2. Looking at the system frequency, we also see the 2003 pessimistic case diverges here as well. Whereas we do have frequency recovery much closer to 60 hertz for the category 3 case than for the category 1 and 2 case. Now, you may be asking, well, you had this fault on the system. Why is the frequency going up instead of going down? And so this is that FIDVR that we were talking about earlier, the fault-induced delayed voltage recovery. And this happens basically because you have low voltage at a number of different locations. And so the static load actually decreases. And then you have these stalled inductive loads, which also reduce the power sort of demands. And so category 1 helps just a little bit, not too much. Category 2 helps a little bit more, but then category 3, sort of compliance on 1547 for the distributed generators shows a very large improvement over the initial frequency deviation. Okay, so now when we sort of loop that back through, those were all single pass results. But if we loop that back through, and now we can take those different versions and rerun the distribution and transmission simulations and sort of converge on answers, what we find here is that the category 3 still has fairly low volt-second scores. And so there's quite a system-wide improvement from this category 3 compliance as opposed to the categories 1 and category 2. So when we do that iteration, we do see in the first sort of iteration, there's a brief dip in the DG output. So this is sort of the momentary cessation of 1547, but then that does improve over time. And as we iterate through, we see that there are corrective actions that can be taken that can prevent that voltage dip from causing a more sustained reduction in the DG output. When we look at frequency, we also see there is quite an improvement even just by the 3rd generation. So you have that initial pulse in the frequency up because of the FIDVR, but then by the 3rd iteration, if we are able to take some corrective actions, we are trending back more toward nominal frequency, though we do have some inner area oscillations that we can see here because this is an averaged frequency of the entire Western interconnection. So the voltage profile also looks quite a bit improved as we iterate through and can take corrective actions. So we see reduced volt-second scores going from about 415 all the way down to 80. And you can see how that impacts the voltage at near the fault location as well as the volt-second scores. So what we've done here is we've developed a loose coupling simulation between the transmission and distribution system simulations and use this to look at the impact of the various IEEE 1547 ride-through criteria and their impact on the distributed generation fleet in the Western interconnection. And so compliance with category 3 provides a much improved response as opposed to category 1, category 2, or the 1547-2003 case, converging to, in this case, a near zero real power loss of DG for this very large fault in the Western interconnection. So thank you very much, everyone, for the time. I'd be happy to answer any questions now, or you can email Wallace or myself at either of these University of Colorado or NREL email addresses.
Thank you, Matthias, for keeping the time. We have still 4 minutes for the questions. In particular, if there are no questions from the attendees, I have one question about the computational burden of such an iterative approach with the results of on the distribution side that is reflected on the transmission side and so on. So clearly the coupling the two models gives a higher accuracy of the response of the DG, and so a clearer way to assess the fulfillment of the ride-through criteria, because we simulate more accurately this response, but of DG, but at the expense of what computational burden. So with respect to a simulation of the transmission system with simplified model of the high voltage and medium voltage grid with the DGs.
It's a fantastic question. So there is obviously a larger computational burden associated with doing the distribution simulations as well. The good news is, because those are individual feeders, that is very easily parallelizable. And so we did some very minor parallelization, allowing us to run, say, 4 or 5 of those at one time, though we are running, over 1,000 different feeders. This was less than, say, a quarter of the total simulation time. And so the big driver here is still the transmission system, though there is a slight increase in computational burden associated with the distribution system simulations.
Thank you. There is one question from the audience. How did you interface the balanced model from PSLF with the unbalanced model from OpenDSS?
I'm sorry, could you, my video cut out there for a second. Could you repeat?
Yes, I can repeat the question. It's from Dan. How did you interface the balanced model from PSLF with the unbalanced model from OpenDSS?
Yeah. So the OpenDSS model is 3-phase, right? So it allows for unbound examination of the distribution systems, because a lot of these systems are connected on single phase sort of laterals within the system. And so the distribution system was unbalanced. We assumed that there was balance at the feeder head or at the substation between those phases. And that is one of the reasons why we did look at a 3-phase fault as opposed to single phase faults, because of that limitation.
Thank you. We have a question from Kate Ben. Do you see a need for the DG fault ride-through criteria to be changed in order to avoid faults turning into major supply disruption events?
Yeah, it's a great question. So 1547-2018 has done a very good job of, in my opinion, anticipating some of the future aspects that we might see. I think one of the issues that we have is that we have a lot of install generation that is compliant with 1547-2003, for example, and may not have been updated in time, and that will be an issue. And then there's the level chosen within category 1, 2, or 3 of 1547-2018. And so my anticipation is that in the next round of 1547 revisions, we will likely see something as resembling category 3 that is going to be mandatory instead of being able to choose between the categories.
Thank you also for this perspective about the standardization.